Saxon's Trigonometry Lesson 8 is about statements of similarity, proportional segments, angle bisectors, and side ratios. In Part A, that's statements of similarity. Now, we've already learned that similar is this symbol here, and they go into some more specifics about if I say triangle ABC is similar to triangle DEF, that I have to make sure I have written them in a specific order that follows the triangle. So I do not wish to rearrange order. The angle A must match up with D. The B must match up with E. The C must match up with F. Also, ABC should be going around the triangle in the correct order. I should not be jumping about. So if this is representing A, B, C, and A was a right angle, and this one is supposed to be the other one, which would be F, D, and E, and this one is the 90 degrees. I see that the A is 90, the D is 90, so they happen to start with those letters, not because they were 90, just that's where they chose to start with the letter A. So its mate over here is the D. And then you could go ACB or ABC, and whichever order you go then needs to match the order this side is listing, or this triangle is listing in. I cannot jump about, so I couldn't do the order A, B, C here and then do D, F, E because I'm not matching up the correct corner. So this was the top point B. It needed to match with the E, the top point here. So as long as they're all lining up and you're not jumping around or mixing them up, this is a correct way to say things. As we talked about before, when triangles are similar, their sides are proportionate, which means they form a fraction. So in example 1, at the bottom of page 61, they give you a triangle where things have been turned into 3 triangles, the big one, the one on the left, and the one on the right. This is labeled B, A, D, and C, and they've marked this one as 90 degrees, and they've marked this large one as 90 degrees. So that tells me that all 3 of these triangles are similar. It says in triangle ABC, segment BD is the altitude or height to the hypotenuse AC. Now there's the 90 degrees, opposite that makes that the hypotenuse. That checks out. An altitude must form 90 degrees where it cuts, otherwise it's not a straight up and down line for height. And if this is 90, this is 90. All right, it says show the following. AD over AB is the same as AB over AC. And because we know that these triangles are proportionate, I can either try to find all of these parts on my own, or I can revert to the chart where I had the big triangle, the right triangle, and the left triangle. I have their hypotenuse, their little leg, and their big leg, and I can fill those in. So from the big triangle, the hypotenuse is AC. The little leg is the AB. I wanted to consult the book because I didn't draw this necessarily to scale. And the big leg is the BC. Now from the triangle on the right-hand side, the hypotenuse is BC, that's this one, and the little leg is BD, and the big leg is DC. Now technically all of these should have segment lines above them, but they're not worrying about that at this point in time, but just to clarify, these are all segments. Now the one on the left, the hypotenuse is AB, the little leg is AD, and the big leg is AB. All right, and what did they want me to conclude? AD over AB. So I am looking for, where do I have an AD here matching with an AB here. Okay, so this is the numerator, this is the denominator. In my chart, that's kind of flip-flop, but it doesn't matter. So I want to pull the matching same two. That would be AB over, that's not what they want, the AC. Okay, so there has to be another one I missed. AD, wait a second. Pretty sure my chart is right. AD, AB. I only had one AD. However, I do have multiple ABs. This one that I first looked at, this one, or this one. So since I know what I need to go to, I need to show that I have the matching column with another AB. So if I use here and this AB, it lines up with the AC, and that is what they wanted. So using these to show the proportion, I have proved what they wanted me to prove. The sides were proportionate. Now moving on to section B, proportional segments. We have done briefly these before, and they go through showing you on the bottom of page 62 that if I have triangles formed with parallel lines, the sides are acting as transversals that are cutting through these parallel lines. So I know that the sides can match up proportionally. And yeah, they just show you the little triangle on the top compared to the big triangle on the bottom. They wrote them out separate, but basically you're doing the comparison of those sides. I can have more than just two parallel lines. So on the top of page 63, they show you multiple parallel lines can form. So if I have a transversal here and a transversal here, even if I don't show that eventually those transversals will connect, ultimately they will at some point connect and form a series of triangles. So even if they're not drawn to look like triangles, they are. So they fit the same rule as the triangles because ultimately they are. So all of their sides can be written in proportionate segments as needed. So I can pull this one to this one, this one to this one, these bottom two, these bottom two, these two. However my combination is, they are all proportionate. Now, in example 2, they say solve for a 3 parallel. They have their 2 transversals. They labeled this one x plus 1, this one 13, then x plus 4 for that one in there, and 19 for that one in there. So we're going to set it up as a proportion to solve for the x's. X plus 1 over 13 equals x plus 4 over 19. And then we cross multiply. So 19 times, we're going to distribute 19 times x, 19 times 1, 13 times x, 13 times 4, 52, I believe. Then I'm going to move this 13 to this 19 so that it's not negative. 19 minus 13, 6x equals 19 taken away from 52 is 33. Divide by 6, x equals, and of course that doesn't go evenly, but they'll both reduce by 3, so that would take me down to 11, and 6 divided by 3 is 2. And that is the answer for x that they're looking for. Okay. On section C, angle bisectors and side ratios. They are trying to prove to you basically why they form proportions as we've been talking about. Okay, so as a quick kind of a thing, if this angle is bisected into 2 equal parts, then do I have similar triangles? Well, I also know that if these are cut into equal parts, then this side and this side have to be in relationship should technically be the same length. This side is shared, and so I have 3 parts that are in either the same or a good relationship. Therefore, I know the triangles are similar, and I can do proportions out of their sides. So yes, if I have an angle that has been bisected, I know that I'm dealing with similar triangles, and I can therefore do the same proportion that we've been talking about. Now, I just did a quick reference to it here. On page 64, they do an optional proof in which they try to show you the same thing in a different kind of proof, making another triangle off of here. If you wish to study that, you are more than welcome to. You understand that the rule works, you're going to use the rule, and you can study the proofs if you so desire. Example 3 and 4 are on page 64. So in triangle ABC from example 3, segment BD, and I'm going to use this graph here. So let's label A, B, C, D. The angles at the top have been marked. This is an X and this is a 12. Okay. Segment BD is the angle bisector of angle B. Find X. All right. Oh, I didn't label. This side was 10 and this is 15. So we are going to set up a proportion because we have bisected angles. So we have X from this triangle matching with 12 from the other side, then 10 matching with 15, and a quick cross multiply gives me 120 equals 15x. Divide by 15, and x is 8, and we've solved what they asked for. Example 4, same thing. This time they've flipped it on its side when they drew it. So rather than redrawing the triangle, I'm going to look to see, can I line up some parts here? So I do have an angle that's been bisected A. Then the 6 is matching with the 14 from the other triangle, and the X is multiplying with the 20. Let me stop here and clarify one quick thing. I do not wish to flip-flop the order in which I'm writing these. So if I choose to start with the one on the right, then I need to keep the other one, the one on the right. Or in this example, if I started with the 6, which was kind of the upper part of the triangle, I need to make sure I'm matching on the other side with that same 14, and so on. And I don't want to flip it. And I certainly don't want to make this 20 over x because I've changed the order of things. Since I started with this one at the top, I want to make the next part from the top. All right, so just to clarify, don't intermix things. It'll throw off your answers. 6 times 20 is 120, and that equals 14x. We're dividing by 14. That doesn't go evenly, but I'm going to reduce it down by what can go into 14 and 120. 2. So that's going to take me to 60 and 7, and that's as far as it reduces, and that is the answer.